Hello and welcome to Windows Forensics and Tools. My name is Adalberto Garcia and I will be guiding you through this course. Here we're going to learn about digital forensics and some helping tools with a focus on the Windows operating system. Now I would like to a little time to introduce myself. My name is Adalberto Garcia. I'm a certified computer hacking forensics investigator. I have a master's degree in information security and privacy, and I always believe that information moves the world, and the way that this data is delivered to people can have a great impact in the society. I'm here to help you in this learning process, and I invite you to connect with me on Twitter or message me if you have any question. You're probably wondering, why should I take this course? If you're a computer science student or professional looking to jump into the field of information security, or if you're a security expert already looking to improve your understanding of Windows forensics, this course is for you. Prerequisites needed to be successful in this course includes basic understanding of digital forensics and the Microsoft Windows operating system, basic computer skills, and knowledge of IT and a willingness to learn. So here are the course modules with the topics that we're going to cover in the course. In Module 1 I will explain what Windows Forensics is and why it is important. Is it easy? Is it difficult? We're gonna see an introduction to Windows and digital forensics. We're gonna cover some common myths about Windows forensics, and we'll also learn about the methodology for digital forensics, the different steps that we need to do in order to perform a forensics examination and analysis. In Module 2, I will explain about Windows imaging, the different principles, the structure of Windows operating systems, as well as the physical drive nomenclature in Windows and the logical drive nomenclature in Windows, and some Windows device names. In Module 3, we are going to perform some hands-on exercises imaging with DD. I'm going to explain what DD is, its basic operation, some DD commands, and what can you do with this tool. We are also going to see some DD logical drive examples, covering physical memory, how to look at memory, and what can you find when analyzing it. Module 4 will be about some memory analysis tools in Windows. I will define each tool, what are they for, their capability, and the basic commands. At the end, we are going to have some labs as hands-on experience and some questions in order to test your knowledge. In Module 5, we're going to learn about the security identifier in Windows, what it is, its structure, and what can we learn from it in a forensics examination. Module 6 is the system registry, which is a very important place to look when performing a forensic examination. I'll explain the different hives, what can you find in them, some new registry hives added in Windows 8, and the registry root keys. In Module 7, we will cover analysis of the evidence, some general registry info to look for, footprints, search history, URLs, commands executed in the machine as well as files. We'll be studying a particular Windows tool that will help us to discover or analyze the evidence. I will be showing you how to perform this process and guiding you to get a better understanding of it. Module 8 is the Windows Prefetch and other Windows essentials. You will be learning the definition and how it is populated, as well as the functionality and the difference according to the version of the operating system. Following with the Windows Essentials, in Module 9, you will see the restore points and other key aspects in a forensics analysis, in which we can discover so many secrets about the machine. We'll be analyzing the registry of the past, how is this the best place to look, and how can we take advantage of this. Some registry keys are present in this module, as well as some Windows integrated tools, which I will be showing you. In Module 10, we'll be learning all the discoveries that we can make by analyzing the recycling bin, another of the Windows essentials. As you probably know, this is where the deleted files go in Windows. We'll see how important it is, where can we find it, and also how it changed from one version to another. In Module 11, we will cover some pertinent files. We'll be analyzing some Microsoft Office files, pictures, and browser information. I will be guiding you through labs in order to get you to gather some important information as evidence which can be vital in a forensics examination. Some tools, which I'll explain in the same module, will be used to perform this process. Module 12 will be about Windows artifacts, some additional places to look when analyzing a Windows machine such as cookies, the desktop folder, address book, application data, and so much more. I'll explain where can we find this information and what data can we extract from them. It is very important that a forensic examiner knows the different places to look for specific information, because it can reduce time and effort when performing a forensics analysis. In Module 13, we'll learn about USB store and how can we analyze it, what information can be extracted from it, and how important it is. Additionally, we'll see some tools to analyze this file. Module 14 is about steganography, which if you don't know what it is, don't worry because I will explain the definition, some history, how it differs from cryptography, and of course, how this fits in the universe of digital forensics. You will be using some tools to hide and extract information using steganography. And finally, in Module 15, you will analyze the structure of email, which is known as email forensics. We'll be analyzing what crimes have been discovered just by examining the information in electronic mails. For this, we need to know how an email is composed and where can we find them in a Windows machine. So, how is this course structured? We're going to have video lectures, of course, and some labs to give you hands-on experience. We're also having some pre- and post-assessment questions in order to test your knowledge. You should have some downloadable resources as supplementary materials to help you out in your studies. In the next section, we're going to start with Module 1, the basics, some definitions and common myths about Windows forensics. Is it easy? Is it difficult? We'll see. We'll be also analyzing the general forensics methodology, and so much more. Hi, welcome back to the course. In the last video, we did a short introduction of who I am, and we also talked about the modules that we're going to cover in this course, the different topics, and the structure of the course, so you know what to expect. If you haven't watched the previous video, feel free to pause this one and watch it so you understand where we are going with this. In this video, we're going to cover the basics about Windows forensics. We're going to talk about what is digital forensics in general, a brief introduction to Windows, and with this, I'll introduce the concept of Windows forensics and why it is important. I will also explain some common myths about Windows forensics. Here is a quick pre-assessment question for you. What other name is also known digital forensics? Is it A, logical forensics? Or B, machine forensics? Or maybe C, computer forensics? Or D, cable forensics? If you say C, computer forensics, you are correct. The terms computer forensics and digital forensics are often used interchangeably to refer to the investigation of any computer or computer-related device or digital device for legal purposes. So, what is digital forensics? Digital forensics, or sometimes called computer forensics, is the application of scientific investigatory techniques to digital crimes and attacks. It is a crucial aspect of law and business in the Internet age and can be a rewarding and lucrative career path. It is defined as the identification, preservation, examination, and analysis of digital evidence, using scientifically accepted and validated process, and the ultimate presentation of that evidence in a court of law to answer some legal questions. The term is sometimes used to describe any sort of investigation of cyber attacks, even if law enforcement or the court system aren't involved. Digital forensics specialists work in both the public and private sector. From this definition, we can say that digital forensics is not just one single process, but a group of tasks and processes in the investigation. In the digital forensics investigation practices, there are over hundreds of digital forensics investigation procedures developed all over the world. Each organization tends to develop its own procedures. Some focus on the technology aspects in data acquisition, while others focus on the data analysis portion of the investigation. Today, digital forensics is an important tool for solving crimes committed with computers, for instance, phishing and bank fraud. as well as for solving crimes against people where evidence may reside on a computer, for instance, money laundering and child exploitation. Forensic tools have also become a vital tool for information assurance because of their ability to reconstruct the evidence left by cyber attacks. Okay, we have defined what digital forensic is, but it's also important to know what digital forensic is not. It is not about finding criminals, because it is about finding the evidence of value. It is not proactive security. It is reactive to an event or request. And it is usually not quick, because modern systems and disks have major capability, which could take a lot of time when processing this kind of information. Now, let me give you a brief introduction to Windows. I'm sure that many of you know, but it is important to know, or remember if you already know, what Windows is and its functionality in order to know how to work with it. Windows is a computer operating system developed by Microsoft Corporation to run personal computers. Approximately 90% of PCs run some version of Windows. The first version of Windows, released in 1985, was a simple graphical user interface offered as an extension of Microsoft's existing disk operating system, or MS-DOS, based in part on licensed concepts that Apple Inc. had used for its Macintosh system software. Windows, for the first time, allowed DOS users to visually navigate a virtual desktop, opening graphical windows, displaying the content of electronic folders and files with the click of a mouse button, rather than typing commands and directory paths at a text prompt. Subsequent versions introduced greater functionality, including native Windows File Manager, Program Manager, and Print Manager programs, and a more dynamic interface. Microsoft also develops specialized Windows packages, including the networkable Windows for Workgroups and the high-powered Windows NT aimed at businesses. The 1995 consumer release Windows 95 with fully integrated Windows and DOS and offer a built-in internet support, including the World Wide Web browser Internet Explorer. With the 2001 release of Windows XP, Microsoft united its various Windows packages under a single banner, offering multiple editions for consumer, businesses, multimedia developers, and others. Windows XP abandoned the long-used Windows 95 kernel, which is a core software code, for a more powerful code base and offered a more practical interface and improved application and memory management. The highly successful XP standard was succeeded in late 2006 by Windows Vista, which experienced a troubled rollout and met with considerable market resistance, quickly acquiring a reputation for being a large, slow, and resource-consuming system. Responding to Vista's disappointment adoption rate, Microsoft in 2009 released Windows 7, an operating system whose interface was similar to that of Vista, but was met with enthusiasm for its noticeable speed and improvement and its modest system requirements. Windows 8 in 2012 offered a start screen with applications appearing as tiles on a grid and the ability to synchronize settings so users could log on to another Windows 8 machine and use their preferred settings. In 2015, Microsoft released Windows 10, which came with Cortana, a digital personal assistant like Apple's Siri, and the web browser Microsoft Edge, which replaced Internet Explorer. One common myth is that Windows Forensics is easy. Unfortunately, it is not. This because of the internal structure of a Windows-based operating system. Windows does not allow easy access to many of the physical layer devices, which is needed if you want to do a bit-level operations, unless you use a third-party software. Windows also has many undocumented features. It is, however, the most commonly analyzed platform in computer forensics, and is harder to interpret attacks. New forensics challenges arise with the introduction of newly released and latest operating systems, while on one hand, these newly released version of Windows are aimed at making things easier for users, many of the functions performed by the operating system can actually be used against the user. The average user is mostly unaware of the fact that their newly upgraded operating system is leaving tracks of their activity. The importance of Windows forensics lies in the fact that Windows is the most widely used operating system, because people may use Windows widely to commit crime as well. Windows provides large number of locations with rich forensics artifacts. These artifacts can help investigators to identify easily whether a crime is being occurred. With the evolution of Windows, forensic soundness also improved. As an example, from Windows XP to 7, there is a major change in the Windows registry. Change in the architecture will be a challenge for investigators. Therefore, it is important to identify what are the forensically sound differences and similarities in each version of Windows. Okay, here's a quick question for you. Which one is not true about Windows? Do you think A has many undocumented features, or B does not allow easy access to the physical layer, or maybe C, a change in architecture represents a challenge for investigators, or D, it is easier to interpret attacks? If you say D, you are correct. The changes in the architecture and different versions of Windows make it harder to interpret attacks. In the next video, we are going to analyze the forensic investigation methodology and its different steps or activities. Hi, welcome back to the course. So in the last video, we talked about some concepts and basic information. We defined what digital forensic is and how it is sometimes called computer forensics. We also analyzed the Windows operating system and discussed some common myths that people tend to think about the system. Now, in this video, we're going to study the forensic investigation methodology, the different steps, and the importance. Following a standard methodology is crucial to successful and effective computer forensics. Just as professional programmers use a programming methodology, computer forensics professionals should use an investigative methodology. A standard methodology will provide for protection of evidence and some common steps that should be followed in the investigation process. The SANS Institute, which is a private US for-profit company founded in 1989 that specializes in information security and cybersecurity training, developed an 8-steps methodology that will help the investigator to stay on track and assure proper presentation of computer evidence for criminal or civil case into court, legal proceedings, and internal disciplinary actions, as well as handling of malware incidents and unusual operational problems. The purpose of these 8 steps is to respond systematically to forensic investigations and determine what happened. A similar process exists and was created by the National Institute of Standards and Technology, known as NIST. This special publication is consistent with SANS methodology and reflects the same basic principles, differing on the granularity of each phase or terms used. Other similar methodologies are described in the ISO 27041. Okay, here's a quick question for you. How many steps are there in the forensic investigation methodology developed by SANS? Do you think it's A, 3 steps? Or maybe B, 5 steps? Or is it C, 8 steps? Or D, 10 steps? If you say C, 8 steps, you are correct. Now let's analyze the 8 steps in a forensic investigation. Normally, the computer forensic investigation will be done as part of an incident response scenario. As such, the first step should be to verify that an incident has taken place, determine the scope of the incident, assess the case, know what is the situation, the nature of the case, and its specifics. This preliminary step is important because it will help determining the characteristic of the incident and defining the best approach to identify, preserve, and collect the evidence. It may also help justify business owners to take a system offline. Then it follows the system description, or the step where you start gathering data about the specific incident, starting by taking notes and describing the system you are going to analyze. Where is the system being acquired, what is the system role in the organization and in the network. Outline the operating system and its general configuration, such as disk format, amount of RAM, and the location of the evidence. In the evidence acquisition, you should identify possible sources of data, acquire volatile and non-volatile data, verify the integrity of the data, and ensure chain of custody. During these steps, it's also important that you prioritize your evidence. and engage the business owners to determine the execution and business impact of chosen strategies. Because volatile data changes over time, the order in which data is collected is important. Please note that all this data should be collected using trusted binaries and not the ones from an impacted system. After collecting this volatile data, you go into the next step of collecting non-volatile data, such as the hard drive. To gather data from the hard drive, depending on the case, there are normally three strategies to do a bitstream image. Using a hard drive device like a write blocker, in case you can take the system offline and remove the hard drive. Or using an incident response and forensic toolkit. Or using a live system acquisition that might be used when dealing with a encrypted system or systems that cannot be taken offline or only accessible remotely. After acquiring data, ensure and verify its integrity. You should also be able to clearly describe how the evidence was found, how it was handled, and everything that happened to it. Note that as part of the investigation analysis, the following steps work in a loop where you can jump from one into another in order to find footprints and tracks left. After the evidence acquisition, you will start doing your investigation and analysis in your forensic lab. Start by doing a timeline analysis. This is a crucial step and very useful because it includes information such as when files were modified, accessed, changed, and created in a human-readable format. This is known as a MAC-time evidence. The data is gathered using a variety of tools and is extracted from the metadata layer of the file system and then parsed and sorted in order to be analyzed. Timelines of memory artifacts can also be very useful in reconstructing what happened. The goal is to generate a snapshot of the activity done in the systems, its date, the artifact involved, actions, and source. In the media and artifact analysis, the investigation should be able to answer questions such as what programs were executed, which files were downloaded, which files were clicked on, which directories were opened, which file was deleted, and many others. When analyzing a Windows system, it can be created as super timeline. The super timeline will incorporate multiple time sources into a single file. The investigator must have knowledge of file systems, Windows artifacts, and registry artifacts to take advantage of this technique that will reduce the amount of data to be analyzed. Memory analysis is another key analysis step in order to examine rogue processes, network connections, and many others. Beware of anti-forensic techniques such as steganography or data alteration and destruction that will impact your investigation analysis and conclusion. The string or byte search will consist into using tools that will search the low-level raw images. If we know what we are looking, then we can use this method to find it. It's this step that we use tools and techniques that will look for byte signatures of known files known as magic cookies. It is also in this step that you do string searches using regular expressions. In the data recovery, we'll be looking at recovered data from the file system. Some tools can be used to analyze the file system, data layer and metadata layer, analyzing the slack space, unallocated space, and in-depth file system analysis is part of this step in order to find files of interest. Carving files from the raw images based on files headers using tools is another technique to further gather evidence. Reporting the results is a key part of any investigation. Consider writing in a way that reflects the usage of scientific methods and facts that you can prove. Adapt the reporting style depending on the audience and be prepared for the report to be used as evidence for legal or administrative purposes. Alright, just one simple question. In which of these steps the investigator should analyze the slack space, unallocated space, and file system? Is it A. Data recovery, or B. Reporting results, or maybe C. String or byte search, or D. Verification? If you said A. Data recovery, you are correct. So in this video we cover the 8-step forensic investigation methodology and analyze each of them. In the next module, we are going to study about Windows imaging, some principles, the logical structure of a Windows operating system, and the physical drive nomenclature. Hello and welcome back to the course. In the last module, we went over some of the basic information that you should know to be successful in this course. We defined what Windows is as an operating system, as well as the forensic methodology. We also talk about Windows forensics in a general way and what is the importance of it. So if you haven't watched that module, please pause this video and watch module 1 as it is very important in the following lessons. In this video, we're going to go over a pre-assessment question for Module 2, and after that, we're going to cover Windows imaging and analyze the digital and physical structure of the operating system. So, here's a pre-assessment question for you. What is a forensic image? Do you think it's A, a direct copy of a physical storage device, or maybe B, a backup of active Windows folders, or maybe C, a duplicate of the files in the operating system, or D, a Windows restore point? If you said A, a direct copy of a physical storage device, you are correct. We are going to see why next. Imaging is important to preserve original evidence. For instance, if it is a criminal investigation or it might end up in litigation. Since forensic activities typically alter potential evidence like file access times. Ideally, you should immediately make a duplicate image of the original drive and do forensics on the duplicate. This might require installing the drive with the duplicate image in the suspect computer and booting from the duplicate drive. So make sure that the drive used to make the duplicate has the same interface as the original. Label the original and store it in a locked and secure location. A forensics image, also called a forensic copy, is a bit-by-bit, sector-by-sector direct copy of a physical storage device, including all files, folders, and unallocated free and slack space. Forensic images include not only all the files visible to the operating system, but also deleted files and pieces of files left in the slack and free space. When imaging a Windows operating system, the same forensic principles apply as when imaging any other system. We can use even the same tools as physical drive images and logical volumes can all be imaged with DD.exe. If you don't know what DD is, don't worry, we're going to cover it later on this course. Not all imaging and backup software create forensic images. Windows Backup, for example, creates image backups that are not complete copies of the physical device. Forensic images can be created through specialized forensic software. Some disk imaging utilities not marketed for forensic use also make complete disk images. The image is verified using MD5 WinMD5, or any other similar tool. A MD5 hash or checksum or message digest is a 128-bit summary of the file contents represented by 32 hexadecimal digits. Files with different MD5 sums are different. Only very exceptionally and usually with the intent to deceive are those with the same sums different. On Windows, all files are read in binary mode, as the MD5 sum utilities there do. The MD5 message digest algorithm takes an input, in this case a file, and produces a 128-bit or 16-byte output, which can be represented as a string of 32 hexadecimal values. This output is a fingerprint or message digest for the file. This is a good way to both verify that the file has not been damaged during electronic transfers and also to verify that the file we're getting has not been tampered with. We need to look at the structure of the Windows operating system. The first physical drive is referred to as hard disk volume 0 and subsequent drives as 1, 2, 3, etc. When you're looking for computers on your network neighborhood, you may have noticed that your local drive is represented by 2 backslashes followed by a dot. Please don't forget to check the references and supplementary material, and in the next video we're going to analyze the logical drive nomenclature on Windows and some commands to extract and mount disks. Hi, welcome back. In the last video we studied what imaging is, why it's important, and how can you check the integrity of a Windows image. We also learned about the physical drive nomenclature in Windows. Now we're going to learn about the logical drive nomenclature. And as usual, I'm going to ask you some quick questions in order to test your knowledge. A very well-known and explained analogy is that a computer running a Microsoft Windows operating system organizes its data like you would organize files in a file cabinet. Each cabinet has multiple drawers. Each drawer contains folders. Each folder contains important papers that you need to file away.  The Windows file system structure parallels this type of organization. Based on the file cabinet scenario, each cabinet drawer is represented as a logical drive on a Windows computer. For example, the logical drive C is usually where your personal data and system data is stored. The D drive may contain files used for computer recovery that should only be managed by a system administrator. The E drive may give you access to a DVD player. When an external device such as a digital camera is plugged into a Windows computer, a new logical drive F may appear, which gives you access to the photo files of the camera. The physical volume or partition on a hard drive is commonly referred to as a drive letter. For instance, C is the common value for the system's main partition. In Windows, the entire drive C or mount point is the letter C, represented by two backslashes followed by a dot, followed by a backslash, and the letter C followed by colon. To access or extract this, we may have to specify the device, the hard disk, and the partition. We can also use the unique volume name. A file system enables applications to store and retrieve files on storage devices. Files are placed in a hierarchical structure. The file system specifies naming conventions for files and the format for specifying the path to a file in the tree structure. Each file system consists of one or more drives and a dynamic link library that define the data format and features on the file system. File systems can exist on many different types of storage devices, including hard disks, jukeboxes, removable optical disks, tape backup units, and memory cards. All file systems supported by Windows have the following storage components: volume, directories of folders, and files. The volume is a collection of directories and files. The highest level of organization in the file system is the volume. A file system resides on a volume, which contains at least one partition, which is a logical division of a physical disk. A directory is a hierarchical collection of directories and files, and the file is a logical grouping of related data. Before continuing, here's a quick question for you. Which of these definitions explain what a file is? Do you think it's A is a collection of directories and files, or B, a hierarchical collection of directories and files, or probably C is a logical grouping of related data, or D, none of the above? If you say C, you are correct. A file is a logical grouping of related data. Let's analyze what directories are. A directory is a hierarchical collection of directories and files. The only constraint on the number of files that can be contained in a single directory is the physical size of the disk on which the directory is located. Some common folders that come by default on a Windows environment include documents, pictures, music, videos, and downloads. The document folder is a logical place to store word processing files, spreadsheets, and presentations. The pictures folder is appropriate for digital pictures that you created, copied, or scanned from external sources such as email, scanner, internet, or digital camera. The music folder is suitable for music files that you downloaded from the internet, ripped from a CD, or composed with a music program. The videos folder is proper for videos downloaded from the internet, copied from a camcorder, or created from a movie maker software. The downloads folder is recommended for programs and files downloaded from the internet. You may also create folders and subfolders. Microsoft Windows uses a file naming convention where the file name is delineated by the backslash sign. A file object provides a representation of a resource, either a physical device or a resource located on a physical device, that can be managed by the system. Like other objects, they enable sharing of the resource, they have names, they are protected by object-based security, and they support synchronization. The system also enables reading from or writing to the resource. Papers and items filed inside a physical file cabinet folder are represented as files in Microsoft Windows environment. A Windows file name can have up to 260 characters. A Windows file usually has a file extension, which helps Windows understand what type it is and how to read it. A regular word processing file with a .txt file extension may invoke a Windows Notepad or WordPad program to open it. A picture file with a JPG file extension may invoke a Windows Picture Viewer program. In naming a Windows file, you should avoid these characters such as slash, the backlash, the interrogation sign, and many others. As we analyzed before, a file system enables applications to store and retrieve files. A Windows application is a collection of executable programs and supporting files. For instance, Microsoft Word is a well-known Windows application. A process is a running instance of a Windows application. Note that most applications allow the user to run multiple copies of the same application at the same time. Each running instance is a separate process with its own memory space. To be more specific, a process is a running instance of an application, together with a set of resources that are allocated to the running application. A thread is an object within a process that is allocated processor time by the operating system in order to execute code. In short, threads, not processes, execute program code. Every process must have at least one thread. The purpose of threads, of course, is to allow a process to maintain more than one line of execution, that is, to do more than one thing at the same time. In a multiprocessor environment, which is a computer with more than one CPU, Windows can assign different threads to different processors, providing true multiprocessing. In a single processor environment, the CPU must provide time slices to each thread that is currently running on the system. Okay, here's a post-assessment question for you. What is the common value used for the system main partition? Is it the letter A, or B, or C, or D? If you say C, you were paying attention. Let's see. Here is a summary of Windows device names. As we analyzed, in the Windows world, drives can be identified by their name, such as Windows 7 OS, etc., and their device letter, such as C, as we have seen before. The important thing to remember is that Windows really only cares about the drive letter. That has to be unique. You can't have two drives labeled E, for instance, on the same computer. The name, on the other hand, is just for convenience. Windows displays it and lets you edit it. But the operating system doesn't use it when selecting which drive to access. That's why you can have two more drives with the exact same name without confusing Windows. So the local machine is represented by two backslashes followed by a dot. The C volume with the letter C, the D volume with the letter D, and so on. But what about drive A and B? Their absence is a historical relic. Those letters were originally set aside for floppy drives. The first physical disk is represented as hard disk 0 and the second physical disk as hard disk 1. We can also identify each volume by the unique volume name. For more information, don't forget to check the reference and supplementary material. In the next module, we're going to analyze imaging with DD. I'll explain what DD is and the syntax, with some hands-on experiences on how to image disks. Hi, welcome back to the course. So along this module, we have defined what imaging is and how you can check the integrity of an image file. So if you haven't watched that video, feel free to pause this one and go over it before doing this lab, as it has some definitions that you should know. In this lab, we're going to learn how to verify the integrity of a file by checking its MD5 hash value using WinMD5. An MD5 hash or checksum or message digest is a 128-bit summary of the file content represented by 32 hexadecimal digits. Files with different MD5 sums usually are different. So for this lab, you will need a web browser in a Windows environment. In this case, I have Google Chrome in a Microsoft Windows operating system, specifically Windows 10. You will also need a compressor program, like WinZip or WinRAR. So first you will need to open a web browser and search for WinMD5. You can go directly to the website www.winmd5.com. In the website, you can download the tool by clicking WinMD5 freeware download. Open it. You should open the file named winmd5.exe. So in here what we're going to do is we're gonna select a file previously created to check the MD5 checksum value. We have this file named helloworld.txt, and now what we should do is you're gonna write down or copy this MD5 checksum value, and we're gonna paste it over here and save it for later. So we now are gonna make a copy of the file used with a different name. Let's put it hello me. Now we're gonna check the integrity of this file. We're gonna check the MD5 value of this new file named hello me. We're gonna browse and select this hello me file. As we see, the MD5 checksum value didn't change, but we're gonna copy this value and paste it in the document. Now we're gonna copy the previous value and we're gonna put it in this field named original file MD5 checksum value, and we're gonna click on verify, and it matched. So are the two hashes identical? Yes, as we see, these two values are the same. And why is that? Generally, two files can have the same MD5 hash only if their contents are exactly the same. Even a single bit of variation will generate a completely different hash value. In this case, we didn't modify the content, just the name. This tool can be used to verify the integrity of an image file. Generally, when we receive an image, we also receive its MD5 hash. What we must do to verify it is use tools like this one to check that the image hasn't been modified or damaged, which is important as well for preserving the evidence and demonstrating its integrity in court. In the next module, we are going to study how to generate and work with image files. Hi, welcome back to the course. So in the last module, we defined what an image is in a forensic investigation and how you can check the integrity of an image file. We also went over some of the physical and logical structure of a Windows operating system. In this module, we are going to keep studying imaging but from a different perspective. You will learn what DD is and how it can be used in a forensic investigation. We will see what an image can reveal and how can you take advantage of this. So before starting, a quick pre-assessment question for you. What is the main purpose of DD? Do you think it's A. Convert and copy files? Or B. Analyze the evidence in court? Or maybe C. Create bugs and viruses? Or D. Test the integrity of a file? If you said A. Convert and copy files, you are correct. It is true that DD can be also used for creating images. We will analyze that later in this video. Okay, but what is DD? DD is a utility that copies files from the standard input to the standard output by default, with a user-selectable block size, while optionally performs conversions on it. It reads the input one block at a time, using the specified input block size. It then processes the block of data actually returned, which could be smaller than the requested block size. It shall apply any conversions that have been specified and write the resulting data to the output in blocks of the specified output block size. You can use this command for copying partial files. You can specify the block size, skip count, and the number of blocks to copy. Sizes are in bytes by default. You can append the letters W, B, or K to the number to indicate words, which are 2 bytes, blocks, there are 512 bytes, or K, which is 1024 bytes. When DD is finished, it reports the number of full and partial blocks read and written. Although DDE is a command line utility originally for Unix-like operating systems, there is a version which allows the flexible copying of data under a Windows environment. This is the structure of a DD command. The BS is the block size. The block size can be specified in bytes. If the block size operand is specified and no conversions are requested, the data returns from each input block shall be written as a separate output block. If the read returns less than a full block, the resulting output block shall be the same size as the input block. If the BS expression operand is not specified, or a conversion is requested, the input shall be processed and collected into full-size output blocks until the end of the input is reached. The default block size is 512, which will work for most files and devices, but the copy will be a lot faster if you use a large block size. For example, a floppy disk read with BS equals 1K and count equal 1440 takes almost twice as long than if you use BS equals 1440K and count equals 1. Don't make the block size too large because Windows will run out of memory. 1M is probably a good size and upper limit. Most CD or DVDs have a 2K sector size and probably will not work with a block size which is not a multiple of that. Count is the number of blocks to copy. If it is not specified, then the DD will continue until the end of the file or device is reached. On many USB devices, this is not reliable, so you should use size to guess the size of the device. You can also use a suffix here, so count equal 1K will copy 1024 blocks. IF, which means input file, specify the input path name. The default is a standard input. OF, which means output file, specify the output path name. The default is a standard output. Skip is the distance to skip over the input file before reading is commenced. It is in blocks, so the distance will be skip multiplied by the block size. You can also use a suffix here, so skip equals 1K will skip 1024 blocks. You can remember that skip relates to the input file by thinking of a skipping rope. Seek is the distance to seek over in the output file before writing is commenced. It is also in blocks, so the distance will be seek multiplied by the block size. You can also use a suffix here, so seek equals 1K will seek 1024 blocks. You just have to remember that if skip is for in, then seek is for out. Traditionally, when using DD, if you wanted to copy an entire device, you do not specify a block count and DD will read it until the end of the device. If you try to read past the end of the device, the data up to the end of the device will be returned, and if you kept reading, you will get an error message. Windows, however, does not always do this. So size will tell DD to figure out the size of the device and make sure it does not read past that point. This is important for USB sticks, which stop working if you read past the end of them. This is not on by default, because getting the correct size of the device is not always possible. Some devices also keep returning fake data past the end of the device without returning a suitable error code. Windows provides a number of ways to name a device. The list command will output the preferred names. Under NT4, only the device hard disk partition method is available, being partition 0, the entire disk. Under Windows XP, some partitions may not have a volume device. In this case, you can still use the hard disk N, partition N name. Windows 2000 and later have volume devices which are unique, which identify a disk or partition. These are listed along with any mount point that they may be mounted on. Most of the time, this is a drive letter, but it might be a path on another file system. If you want to read the underlying device, do not include the trailing / character. If the volume is not mounted, there is no easy way to identify it, so be careful. Under XP Servipack 2, many partitions cannot be read directly, even if they are not in use. Progress is a non-standard enhancement to DD, which will show you the progress as each block is copied. The processing order in DD shall be as follows. First, an input block is read. Second, if the input block is shorter than the specified input block size, null bytes shall be appended to the input data up to the specified size. The remaining conversions and output shall include the path characters as if they had been read from the input. If the block size operand is specified and no conversion is requested, the resulting data shall be written to the output as a single block, and the remaining steps are omitted. Any remaining conversions shall be performed. These conversions shall operate on the input data independently of the input blocking. The data resulting from input or conversion, or both, shall be aggregated into output blocks of the specified size. After the end of input is reached, any remaining output shall be written as block without padding. Thus, the final output block may be shorter than the output block size. Here's a quick question for you. What can be done using DD? Is it A. Make an image of a floppy disk? Or B. Rip an ISO from a CD? Or maybe C. Read a partition from a USB memory device? Or D. All of the above? If you say D. All of the above, you are right. Let's see some examples on how to perform these activities. Here you can see some examples. For making an image of floppy disk, you can specify A in the input file, as this is the letter reserved in Windows for floppy disks. The same case for writing the image back. In this case, the letter A needs to be in the output file. In the third example, when ripping an ISO from a CD, the command device CD-ROM 0 as the input file will tell DD that the input is a CD. When reading a partition from a USB memory device in the following example, you should specify the unique volume identificatory as the input. But if you read the entire USB memory device, just specify the device hard disk 1 and partition 0 for the input. You can write to any file or block device which Windows will allow you to write to. You can use the standard backslashes with a dot notation for Windows supported devices, or the DD-specific backslashes with the interrogation sign notation to access Windows native devices. You cannot write to a CD with this program. You should get Microsoft CD-Burn from the Windows XP Resource Kit. Note that floppy disks are extremely unreliable. If you get errors, please try another floppy disk or reformatting the disk. Please don't forget to check out the references and the supplementary material. In the next video, we're going to do some exercises to practice the DD commands that we just analyzed. Hello and welcome back. In the last video, we were analyzing the data dumper, DD, and its functionality. You do want to know those concepts for this video, so feel free to pause this one and go back to the previous one for analyzing what DD is. In this video, we're going to analyze how to obtain physical memory in a forensic manner. Conservation of volatile data is one of the most challenging tasks in computer forensics. This is to dump the RAM content of a running computer in a forensically sound manner. In the Microsoft Windows environment, DD provides a convenient way to copy the memory into a file. There is only one flaw. It won't work from Windows Server 2003 Servipack 1 onwards. The data dumper, or DD, relies on a core dump function which creates a special image structure in a keyword equals value format. Therefore, the output file is readable in many tools and applications like the Windows kernel debugger. We need to analyze the pros and cons of this process of forensic RAM dumping with DD. In the advantage, we have that there is no need to install software like kernel mode drivers on the system under examination. DD and the created memory dump usually fit onto a USB memory stick. A simple file format is managed. File offset equals the address in physical memory. Executing the program does not require rebooting the system or any disruption of the service. In the disadvantages, in addition to the fact that this can be done in a recent version of Windows, we also have that the dumped memory has the same size as the RAM. The system continues to run during the dump, resulting in a blurred image instead of a sharp snapshot. Microsoft Kernel Debugger can't handle the file format. There are no publicly available tools to analyze a memory dump. And finally, administrator privileges are required. Physical memory is a exception object which enables us to access the physical memory from ordinary user mode applications in Windows. Fortunately, from a security viewpoint, this exception object can only be opened by members of the administrator group, as we have seen. Unfortunately, also from a forensics viewpoint, all user mode access to it has been blocked in Windows XP 64-bit and Windows 2003, Windows Vista, and followings. We will be studying it anyways, as you may encounter in the forensic investigation some servers or machines where this process is possible, and also it's good to know the full functionality of DD. The syntax displayed will image your physical memory and save it to a file for further analysis. This grabs the system memory until the end of file error. As a result, you will see a benign error reporting when the starting offset of the read goes beyond the range of the addressable physical memory. Any Windows-based debugging tool can analyze a physical memory image after conversion to a Microsoft Crash Dump format. Today, we use commercial tools such as the Forensic Toolkit or FTK or a program called Dumpit from Bunsource. We will analyze these tools later on this course. As usual, here's a quick question for you. When performing a forensic raw dumping with DD, which statement from the following is not true? Do you think it's A. The dump memory has the same size as the RAM, or B. Administrator privileges are required, or C. Executing the program does not require rebooting the system, or D. It will work on a Windows Vista operating system? The answer here is D. Unfortunately, all user mode access to the physical memory has been blocked in Windows XP 64-bit and Windows 2003 Servipack 1 and Windows Vista and followings. Forensics analysis of physical memory is a relatively new field of research. Although there are a lot of software tools for acquisition of systems' physical memory, we need to be careful as software tools will inevitably damage or even override the contents of physical memory. A lot of information on computers, such as the system processes, network information, login information, registry information, open files, configuration parameters, and so on, must be accessed by obtaining and analyzing the target computer's physical memory dump. This will be the main topic in the next module. In this module, we have covered the Data Dumper or DD as a tool for creating forensic image files. We studied the definition, some examples, the functionality, and the syntax. We also analyzed the physical memory and how can we get information out of it. Don't forget to check the references and supplementary material where you will have the chance to practice the topics covered. And join me in the next video where we will be doing some labs. Hi, welcome back to the course. In this module, we have analyzed the concept of the data dumper DD and how we can create image files along with the commands used when using it. In this lab, we're going to learn and practice the basic use of DD by creating image files. DD can duplicate data across files, devices, partitions, and volumes. The data might be input or output to and from any of these. For this lab, you will need a web browser in a Windows environment to download the tool. I have in here Google Chrome on a Windows 10 environment, but feel free to use the browser of your choice. We will also need a USB memory device, which we will image, and a zip reading program. Some versions of Windows come with one built in. If your version of Windows does not, you can get a free program called 7-Zip, or you can also use WinZip or WinRAR, among others. So the first step is opening the web browser. In here I have Google Chrome already opened. So we're going to search for DD for Windows. You can also go directly to the website, which is this first one, chrysocom.net, DD for Windows. We are going to download the last stable version for Windows from the website. In this case is the version 0.5. Then we proceed to download it. And we're gonna save it, in my case, in the local disk D, in a folder named temp. The next step that we're gonna do is we're gonna unzip the file downloaded, and we're gonna extract the content of it. In this case, we're extracting dd.exe. Following, we're going to open a Windows command prompt by typing cmd Next, we're going to change the directory folder in the command prompt to a directory where dd.exe is located by typing cd and the path name. In this case, as it is located in the D disk, we'll type D, and then we'll type cd d and the folder temp. Next, plug the USB drive if it's not already plugged in, and note the letter assigned to it. So as we can see here, I have this USB memory device, which is assigned the letter H. With that note, we're gonna go to the command prompt again, and we're gonna proceed to use dd commands. So by typing the command dd.exe list, you can check the drive and partitions in the computer and see the letter assigned as well as the unique volume ID. So we can see here the C drive, the D drive, the H drive, as well as CD-ROM and the others. Now we're going to proceed to create an image of the USB drive. So in the command prompt, we should type the following command, which is specified in the guide. dd.exe we might as well copy and paste it in the command prompt. So in here, H is the letter assigned to my device, and the path temp usb2.img will be the path of the image file to create. You may want to change these values if they are different in your computer. So be sure that this output file is a valid path file, because if not, it will show an error. So in here, size will tell dd to figure out the size of the device and make sure it does not read past that point. So as you can see, progress will be showing us the progress of the process. So we press enter, and in here we should wait for the tool to create the image. The time will depend according to the size of the file or the drive that we are copying it. So after the file is created, we'll have to answer this question. if are the image file created on the drive the same size. So it is finished. So we shall proceed to the path where the file is located. In my case, it's in the local disk D in the folder named temp. As we can see, there is a new file created in this folder named usb2.image as we put it in the path and in the output file. So if we select this file, we can see that the size in here is very similar to the size of the drive. In the next module, we will be studying how to analyze in detail these image files. Hello, welcome back. So in the previous lab we were analyzing how to create an image file from a USB drive. Now we're gonna rip an ISO from a CD or DVD. For this lab, you will need a web browser in a Windows environment. To download the tool, I have Google Chrome in a Windows 10 environment. You also need a CD or DVD and a zip reading program, such as 7-Zip, WinZip, or WinRAR. If you have DD already downloaded, please skip to step 6. If you not, please go to the DD site www.chrysocom.net and download the last stable version. In here, I have already downloaded the 0.5 version of DD. Save it in your computer and unzip it. My dd.exe file is located in the D disk in a folder named temp. Now you should open a Windows command prompt by typing cmd and change the location to the location where dd.exe is located. In my case, it's in the local disk D, so I'm gonna type D and then cd d temp. Now you should insert the CD or DVD in the computer if it's not already in, and note the letter assigned to it. So for me, I have my DVD drive in the letter E. By typing the DD command list, we can check the drive and partitions in the computer and see the letter assigned as well as the unique volume ID. So if I type that dd.exe list, I should be able to see all the partitions and disks in my computer. So as we can see, the CD-ROM is in the letter E. Now to create an ISO of the CD, I should type this dd command. You should may as well copy it and paste it from the guide. In here, E is the letter assigned to the device, and dtemp.this1.iso is the output file or the path where the new file is gonna be. I also type progress, which will indicate the progress of the process. So I should press enter and wait for the process to be finished. In here the time will depend of the size of the disk, in this case the CD or DVD. After finishing, we need to answer this question again if the ISO file created and the CD are of the same size. So it is finished. Now what we're gonna do is we're gonna check in the folder, in the output folder, in my case temp, there is a new file created named this1.iso, and as we can see, the size of the file is exactly the same as the size of the DVD. Don't forget to check the references and supplementary material for more information, and see you in the next module. Hi, welcome back to the course. In the last module, we were analyzing how to create image files from different devices and drive using the data dumper DD. It is very important that you learn how to create these images, so if you haven't done it, I recommend looking at the videos in the previous module. In this module, we're going to analyze some forensic memory analysis tools and techniques. You will learn why is memory analysis relevant, the pros and cons of some tools and techniques, and how to use them in your investigation. We're going to have some labs for you to follow and practice, and as usual, I will be asking you some questions along the way to test your knowledge. Before starting, here's a quick pre-assessment question for you. Where in the computer resides information such as network connections, command history, or information related to executing applications? Do you think is A, random access memory, or B, local drive D, or C, hard drive, or maybe D, USB drive? If you say A, you are correct. This information is also known as volatile information and can get lost if the computer gets unplugged. Different studies referenced have demonstrated that forensic physical memory analysis has gradually evolved from basic techniques such as string searching to more complex methods. As computer malwares becomes more sophisticated, tools and techniques for memory analysis suffer inadequacies. Given this, it is essential to examine tools and techniques for physical memory analysis. By understanding their behavior, limitation, and advantage, it is possible then to select the most suitable solution. To find digital evidence, traditional forensic procedures examine storage devices such as hard disks by acquiring an exact sector-by-sector copy for later analysis. Even though disk forensics provides file system data such as stored files and installed programs, several reasons prevent from solely applying this method. First, the required time to image a hard disk increases proportionally to hard disk storage capabilities. Thus, imaging large-scale hard disk is not convenient when time is a crucial factor. Secondly, since disk imaging requires unplugging the system, availability of the system is interrupted, which might be expensive and inconvenient for companies. Moreover, all of the volatile information such as network connection, command history, or information related to executing application is lost. This information resides in random access memory or RAM, and it is not possible to access it by means of disk forensics. Therefore, memory forensics becomes the cornerstone to find significant evidence. A differentiation in memory definition should be noted. In Windows operating system, the Windows Manager maps pages in virtual memory to pages in physical memory. This means that the data can temporarily reside in virtual memory and afterwards be allocated at a specified address in memory. That is, physical memory provides the main storage while virtual memory optimizes the use of physical memory. These concepts are relevant, since malware is capable to hide itself without leaving any trace of activity. The mechanisms they apply directly affect the operating system. In consequence, since the operating system is compromised, the mechanism for memory management might be compromised as well. Because of this, it is no longer possible to rely on the information it provides. Early attempts to establish memory scanning techniques clearly declare the need for memory scanning. The essential idea is to obtain reliable information of the system state. Running processes rely on applications that could be manipulated to produce false data. Therefore, the only solution available is to take snapshots of the memory state along with the static memory. Do not forget to create an integrity check using MD5 Zoom before starting any analysis or by running it during the execution of dd.exe. We can achieve this with dd. The following is an example of the syntax. It will copy C drive, calculate the MD5 checksum, and verify the resultant image against the checksum. I recommend looking at the previous module for running dd commands. Feel free to pause the video to take note of the command displayed. Before jumping into tools and techniques for memory analysis, we need to analyze memory acquisition. We have studied how to acquire images with dd, but for obtaining physical memory, dd won't work in most recent versions of Windows. Memory forensics is becoming an essential aspect of digital forensics and incident response. When a system is believed to have been compromised or infected, the investigator needs a convenient way to take a memory snapshot of the host. While analyzing memory requires a set of skills, acquiring memory is not that difficult, all thanks to the new tools available. Dumpit makes this possible, even if the person in front of the affected computer is not technical. One of the major benefits of Dumpit is that it is very easy to use, and any user with administrator privileges can use it. The person needs to simply double-click the Dumpit executable and allow the tool to run. Dumpit will take the snapshot of the host's physical memory and save it into the folder where the tool executable is located. Since Dumpit is a simple tool, it doesn't have any analysis capabilities. Here is where the tools for memory analysis are needed. A crash dump can be the result of instability on the system. Internally, when a crash dump occurs, the system state is frozen and the contents of the physical memory are swapped or copied to the disk. The result is a crash dump file with the contents of the RAM and extra debugging information. Windows provides a keyboard configurable feature to generate dump files. The output file is .dmp format, compatible only with Microsoft tools. This format adds information of CPU state. The advantages of this is that the file obtained from a crash dump is a faultless copy of the RAM, and the disadvantages is that the format is not specifically for forensic but for debugging purposes. Currently, mini dump versions are available. Complete dumps are not available. There are two main issues when configuring the feature. It requires to reload the system for the changes to consider, and its functionality is limited to a specific keyboard driver. We can access this functionality in the control panel of any Windows computer under the System Advanced settings. It is usually located on the Startup and Recovery settings. There are different techniques for memory analysis. One of the most traditional techniques in memory forensics is the search for valuable strings such as password or network addresses that are relevant for the investigation. As the main advantage, we have that it is easy to use, but the disadvantages are that these techniques, except for the clustering algorithms, provide information without an overall context. Mostly, it is inferred by the investigator. It is undesirable to apply this technique without a set of predefined keywords to pursue. Another technique is finding process objects. Techniques based on the detection of processes are a reliable source for finding evidence of malware, since a thread which does not belong to any process is more likely to be a suspicious object. The main drawback relies on the fact that sizes and the values of the structure do change between Windows operating systems versions and service packs. Finding object signatures, it is also a common technique. Object-specific signatures can be used to identify them in memory. The main approach is to scan the pool of signatures to identify hidden objects. We have studied the techniques. Now let's take a look at the tools for memory analysis. MemParser, a tool by Chris Betts, enables the examiner to load a physical memory dump or image of a certain Windows system, reconstruct the process information, and extract data relating to specific processes. The process environment option may include the full path of the executable and command line processes. It has the display loaded DLLs option, which provides a list of dynamic link libraries that were associated with the process in question. It can save the contents of process memory to a file, strings, and other more specific information can also be extracted. Volatility is an open-source memory forensics framework for incident response and malware analysis, useful for analyzing RAM in 32 and 64-bit systems. Volatility's modular design and the fact that it is written in Python allows to easily support new operating systems and architectures as they are released. It supports analysis for Linux, Windows, Mac, and Android systems. It can analyze raw dumps, crash dumps, VMware dumps, virtual dumps, and many others. Okay, here's a post-assessment question for you. Which one is not a technique for memory analysis? Is it A. String searching, or B. Finding process objects, or C. Finding object signatures, or D. Imaging partitions? In here, the answer is D, as imaging partitions and disks is a process that must take place before the analysis. Don't forget to check the references and supplementary material, and in the next video we're going to do some exercises to practice some of the tools that we just analyzed. Hi, welcome back to the course. In this lab we're going to create and collect a full memory dump in Windows using the Windows Crash Dump utility. We need to have a memory dump file before learning some tools for memory analysis. For this lab, you will need a machine running a recent version of Windows. In here we have a Windows 10 operating system. You will also need a web browser to download the tools. Where if it is a virtual machine, a machine in a Cybrary lab, or a machine of your own, log in into your Windows machine. Go to the control panel, in System and Security, select the option named System. In here, click on Advanced System Settings. When the System Property window appears, in the Advanced tab, click on the Settings button under the Startup and Recovery section. Select Complete Memory Dump from the Right Debugging Information drop-down menu. And then clicking OK. Usually it will ask you to restart the computer. Do not restart right now as we are going to do that later. Clicking OK. Now what we're going to do is we're going to open the web browser and download the NotMyFault64.exe by going to the website live.sysinternals.com. Search for the tool named NotMyFault. We're going to download the NotMyFault64 as we are in a 64-bit operating system. Save it in your computer. We're going to save it in the local disk D in a folder named temp. Now open an elevated command prompt window by clicking on the start icon on the bottom left-hand corner. Type cmd, right-click on it, and run as an administrator. Change the directory folder in your command prompt to a directory where NotMyFault is located by typing cd and the path name. As in here, I got it in a different disk. I'm gonna write the local disk D, and then cd and the path, which is temp. That is the folder where the tool is located. NotMyFault is a tool that you can use to crash, hang, and cause kernel memory leaks on your Windows systems. It is useful for learning how to identify and diagnose device driver and hardware problems, and you can also use it to generate blue screen dump files on misbehaving systems. In this case, by typing the following, what we're gonna do, we're gonna crash the computer, and the system will create a large kernel dump file named memory.dmp. After crashing and restarting the computer, we'll need to locate the dump file. To locate the file, press the letter R and the Windows key on your keyboard at the same time. Type system root in the field and then press OK. You will see then the file named memory.dmp. Now we know how to create memory dumps. In the next video, we're going to learn how to analyze this type of memory dump files. Don't forget to check the references and supplementary material for more information. Hi, welcome back to the course. In this lab, we're going to analyze a memory dump file with Volatility, an open source memory forensics framework for incident response and malware analysis. The reason why this type of information is called volatile is because it is stored in the system memory, and when the computer gets turned off, this information in memory disappears. For this lab, you will need a Windows operating system and a web browser to download the tool. You will also need a zip reading program such as 7-zip, WinZip, or WinRAR, and you will need as well a memory dump file. It can be a RAW, vmem, or DMP file, and many others. You can generate one using tools such as DD, Dumpit, or the Windows Crash Dump utility. First, you need to log in your Windows machine and open a web browser because we need to download Volatility from the website. You can go directly to the website volatilityfoundation.org to download it. We're going to download the latest version of Volatility and save it in our computer. I'm going to save it in my local disk D under a folder named temp. Now we're going to unzip it, but just the X file, the exe file that is located in the folder, which is the executable. Make sure that you have the memory dump in the same folder as the tool. In my case, I have this file called memory.vmem in this folder, and this file is the one that I'm going to analyze. Now open a command prompt window by typing cmd in the start menu. Now you will need to change the path or the location to the path where Volatility is located. In my case, it's in the local disk D, and by typing cd and the path name, I'm going to change this location. I have it in my folder named temp. Now we can start typing Volatility commands. By typing image info, which is the first command that we're gonna use, Volatility will give us some information about the file analyzed. The syntax for Volatility is this one in here. First, we need to type the name of the executable, followed by F, which is the file that we're going to analyze, and then the other commands. In my case, I'm gonna type this one here. Make sure that you replace memory.vmain for your memory file. Press enter. And as we can see, Volatility is telling us that this image file corresponds to a Windows XP machine. In this case, the suggested profile are Windows XP Servipack 2, Servipack 3, but By taking a look at the image type or service pack, which is 2, we are now sure that the version of Windows is Windows XP Service Pack 2. Now, to know what profiles are supported by this version of Volatility, you can type the -info command and you will see the list with all the profiles. Let's try it. As you can see, here's the list with all the commands and the profiles supported by this version of Volatility. Now, to see the list of processes that we are running in the machine, when the image file was generated, we will use the command pslist. The syntax is the same, so we need to copy and paste this over there in the command prompt. The only change in here is that we now are going to use the profile to let Volatility know that we are dealing with a Windows XP Service Pack 2 machine. Make sure to change this profile to the profile in your image file or memory file. pslist will give you the process name and ID and more information about the processes, such as the date, when it started, and so on. We can see here the full list of processes. Now we're going to use the command named ps3. This is to analyze the process list in a tree format type. The syntax is the same, but in this case, instead of pslist, we're gonna type ps3 and press enter. You will see the same processes, but with a nicer view and less details. Now we will use the command psscan to analyze the terminated processes. It can be the case that the malware process was not in the execution at this moment. In this case, this command couldn't find it. But with psscan, we can find it. So instead of ps3, we should type psscan. You can see here the list of terminated processes. Now, it can be the case that you may want to save this result in a text file. To save any result to a file, you can type the normal volatility command followed by the symbol greater than and the name of the text file to generate. In this case, I'm gonna name it result.txt and press enter. The file is going to be saved in the same folder where the tool is located. Let's check it. And we can see that there is the result.txt file with the result of the command. By using the command psxview, we can find hidden processes, which will show us a combination of both pslist and psscan. If a process is in psscan but not in pslist, it is probably a hidden process. So the syntax is the same, but the termination in this case will be psx. View and press Enter. And you will be able to see the process list in a more detailed way. As you can see, you can check if the process is in the PS list or PS scanned and many other commands. Another useful command in Volatility is DLL list, which provides a list of dynamic link libraries that were associated with the processes in question. There are many other useful commands in Volatility. You can try typing the command -h to see the complete list of commands or plugins. Don't forget to check the references and supplementary material for more information. And in the next module, we're going to see one of the Windows Forensic Essentials, the security identifiers. Hi, welcome back! In the previous module, we went over some tools for collecting and analyzing memory dump files. We analyzed what are the different techniques, their advantage and disadvantage, as well as how can we generate our own memory dump files using the integrated functionality in Windows. Now, in this module, we're going to learn about one of the Windows Forensic Essentials, the Security Identifiers or SIDs, the definition and what information can we infer from them. A security identifier, commonly abbreviated as SID, is a unique value of variable length used to identify a trustee, which can be an user, a group, a logon session, or other security principal. A security principal has a single SID for life in a given domain, and all properties of the principal, including its name, are associated with the SID. Each time a user logs on, the system retrieves the SID for that user from the database and places it in the access token for that user. The system uses the SID in the access token to identify the user in all subsequent interactions with Windows security. When a security identifier has been used as the unique identifier for a user or group, it cannot ever be used again to identify another user or group. The SID contains information about user rights and privileges, settings, and any other information that is specific to that particular user, and again is a useful piece of information for forensic analysis. It is variable in length and encapsulates the hierarchical notion of issue and identifier. It consists of a 6-byte identifier authority field that is followed by 1 to 14 32-bit sub-authority values and ends in a single 32-bit relative identifier or RID. When displayed textually, the accepted form is this one in here, where S and 1 are literal strings, the identifier authority is the 6-byte value, sub1 through sub-n are the sub-authority values, and RID is the relative ID which identifies the type of SID. The combination of the identifier authority value and the sub-authority values ensures that no two SIDs will be the same, even if two different SID issuing authorities issue the same combination of RID values. Each SID issuing authority issues a given RID only once. In the structure, the identifier authority is an array of 6 bytes which describes which system owns the SID. Windows NT defines 6 identifier authorities, which are the null SID authority, which is used to hold the null account SID, or S100. The world SID authority, which is used for the everyone group. There is only one SID in that group, and is S110. The local SID authority is used for the local group. Again, there is only one SID in this group, and it is S120. The security creator SID authority is responsible for the creator owner, creator group, creator owner server, and creator group. You can identify which SID belongs to this category because they have the number 3 in the identifier authority field. The value 4 corresponds to a security non-unique authority, which is not used by Windows NT. The value 5 corresponds to Security NT Authority, which describes accounts that are managed by the NT subsecurity subsystem. And with Identifier Authority value 9, we have the Resource Manager Authority, which is all that is used for third-party resource managers. Windows allocates RIDs starting at 1000. RIDs having a value less than 1000 are considered reserved and are used for special accounts. For example, all Windows accounts with a RID of 500 are considered built-in administrator accounts in their respective issuing authorities. Well-known security identifiers, or SIDs, identify generic groups and generic users. The following are some universal well-known SIDs. We have the null SID with value S100 and identifies a group with no members. This is often used when a SID value is not known. The word security identifier with value S110 identifies a group that includes all users, even anonymous users and guests. Membership is controlled by the operating system. The local security identifier with value S120 identifies users who log on to terminals locally and are physically connected to the system. The Creator-Owner ID, identified with the values S130, is a security identifier to be replaced by the security identifier of the user who created a new object. This SID is used in inheritable access control entries. The Creator Group ID, with a value of S131, is a security identifier to be replaced by the primary group SID of the user who created a new object. Most applications never need to work with SIDs because the names of well-known SIDs can vary. It is recommended to use the functions to build the SID from predefined constants rather than using the name of the well-known security identifier. For example, in the United States, the English version of the Windows operating system has a well-known SID named Built-in Administrator that might have a different name on international versions of the system. Okay, here's a quick question for you. Based on the identifier authority value, which of the following SIDs correspond to users who log on terminals locally, physically connected to the system? It is A. S100, or B. S110, or C. S120, or D. S130. If you said C, you are correct. The identifier authority with value 2 is local and is used for the local group. There's only one SID in that group and it is S120. We have analyzed security identifiers, its function and structure, and we also know some well-known security identifiers such as the null SID for a group with no members and the word SID, which includes all users in the system. Don't forget to check the references and supplementary material for more information on SIDs. And in the next module, we're going to study the system registry and its hives. You will know what are those hives and why they are useful in a forensic investigation.